biomedical and materials engineering. Let me introduce Sir. Professor Bjorn Schuller is a scientist of electrical engineering, information technology and computer science, as well as he is an entrepreneur. Graduated in the year 1994, followed by the diploma, doctorate, and also state doctorate in the field of signal processing and machine intelligence. He served as adjunct teacher professor in 2012, each in electrical engineering and information technology at the Technical University of Munich, Germany. Here he has also headed as scientific assistant, academic council and junior fellow in machine intelligence and signal processing group at the chair of human machine communication. He is a professor of artificial intelligence at Imperial College London, UK, and holds the chair of embedded intelligence for healthcare and well-being at the University of Augsburg, Germany. He is also co-founding CEO and current CSO of Audioring, that is an audio intelligence company at Berlin, Germany. He is an independent research leader within the Alan Turing Institute and the Royal Statistical Society labs as data analytics and surveillance group. He is a guest professor at Southeast University in Nanjing, China, and permanent visiting professor at HIT, China, amongst other professorships and affiliations. His previous stays include key researcher at Australia and CNRS LIMISI in France. He is a fellow of the IEEE and Golden Core awardee of the IEEE Computer Society, fellow of the BCS, fellow of the ISCA, fellow and president emeritus of the AAAC, and senior member of the ACM. Professor Schuller is an author and co-author of more than 1,000 papers in the peer-reviewed books, journals, and conference proceedings. He has more than 45,000 citations and having H-index 96. It's a long resume of Sir. He is a field chief editor of Frontiers in Digital Health and was editor-in-chief of the IEEE transactions on effective computing amongst manifold further commitments and service to the community. His 40+ awards include having been honored as one of the 40 extraordinary scientists under the age of 40 by the World Economic Forum in 2015. He has received starting grant from ERC amounting to 1.5 million euros, the highest ever grant received as a young researcher. He served as coordinator, principal investigator in 15+ European projects, and he is consultant of companies such as Barclays, Informatics, Samsung, and many more. Thank you, sir, for joining us. Thank you for gracing our occasion. With this introduction, I would like to request the speaker to proceed for his keynote address. Welcome, Schuller, sir. Welcome, sir.
Thank you so much for the kind introduction and many humble words. I am not able to share my screen as of now. So maybe somebody needs to enable screen share. Oh, great. And oh, it doesn't work for some reason. This is bad. Oh, no, I got it maybe. Just a second. Okay, I need to join again, sorry. I'll be back in a second. Can you already see my screen? Yes, I guess so. Can you hear me?
Hello. Hello, sir.
Yeah. Yeah. Hi. Can you hear and see me?
No, sir.
No. But you see my screen or also not?
No, sir. I cannot see your screen. Neither PPT.
And can you see me?
No, sir.
Oh, that's bad. But you can hear me.
Yes, sir. I can hear you.
No video and no screen of mine.
No video, but I can hear you, sir. I cannot see the presentation also. But your voice is clear, sir.
I'm sharing actually the screen and the video. I'm not sure why then you don't get it, unfortunately.
Sir, are you the presenter? Can you see the share tray icon on the screen?
Yeah, and I'm sharing, and my screen is having a red frame, meaning that you should be able to see it. I can try and leave and join again. Do you think that's helping?
Yeah, you can leave and join again.
Let's leave and join again. Let's see if that helps. Hi, do you have a video from me?
Yeah.
You can see me?
Yeah, I'm able to see you.
Cool. Now we only need to make sure you can even see my presentation. Can you see the presentation?
Oh, yeah, now it's visible.
You can see it?
Yeah, now I can see it. It's perfectly fine.
Okay, so sorry so much for this technical problems, and thank you so much again for the kind invitation and occasion to speak to you now on hot off the fire deep learning. And as we are here at the conference in materials manufacturing and machine learning, with a broader scope, I figured that it might be nice to show some applications of what we do in deep learning, and then really talk about some perspectives from a machine learning and deep learning point of view, what should best be done to further cater for the needs of these different applications to advance the quality of these. So with that, the talk is mainly really about deep learning or machine learning in general for a couple of applications. And as said, as we are at a materials focused conference, I thought I'd pick this example for you first: prediction on mechanical properties of non-equiatomic high entropy alloy by atomistic simulation in machine learning. And in this example, what we're doing is using machine learning to basically consider different materials in terms of their molecules and their orientation, and then predict qualities. In particular, this is yield stress and Young's modulus. And the idea is that rather than running a MD simulation, we train a machine learning algorithm to predict what we would get from the MD, from the analysis or the simulation. And what we can get there is things like the actual regression output of yield stress or of Young's modulus, or we can simply get a binary classification output like good or weak. So in other words, we're trying to find good materials by running a machine learning algorithm, which can be very fast once it is trained, rather than running big simulations or actual experiments with materials. And the idea then, of course, is that we need training data. We need already run simulations, but then we want to generalize, of course, for new materials, for new orientations of the molecules and so on. So basically, we're looking at this kind of example here, copper, ferrum, nickel, and so on here as a material to be designed. And we're testing different machine learning models, including deep neural networks, extreme learning machines, support vector machines, so some traditional, conventional approaches, and basically see how good we can be and predicting yield stress, Young's modulus based quality of the material. And these are some results for the particular case of looking into these constellations of materials. And first, what we have is some kind of comparison, as said, between different machine learning algorithms, where extreme learning machines performed very well in our case on the test set. For YS, so the yield stress, and for Young modulus here on the right-hand side. Similarly, kernel extreme learning machines perform very well, but basically what you can see for this best algorithm here is that you can get quite useful results on predicting the qualities of a material that you would be designing with a very quick approach with machine learning rather than with running extensive simulations. And for these 8 combinations, actually 11 combinations of constellations we considered, we found that the machine learning result was satisfying in terms of deviation for yield stress and Young modulus in most cases. So we get more than just the binary good or weak properties of the material. We can actually get close to the running the simulation output. And essentially, of course, this comes as neural networks, and deep neural networks are function learners, and we can estimate highly complex functions. The second example maybe of interest in this context is in fluid mechanics, solving the Poisson equation. And we introduced Poisson CNNs, so convolutional neural networks, for the solution of the Poisson equation on a Cartesian mesh. We have also been looking into other kind of neural architectures in this paper. And maybe that is one of the major points I want to come back to later on, that one of the problems is, while we can provide solutions which are useful, which are giving good results, a major drawback is still that it needs experts to design these networks. But as said, we will come back to that later on. So what we have in this case is we have the right-hand side of the Poisson equation as an input, domain info from our fluid mechanic problem to be solved. We have some top button left and right BCs as an input, and then we have some kind of neural network architecture, which, as said, is still unfortunately expert crafted. So this is not automatically learned or shaped yet. We have some homogeneous Poisson neural network here and a Dirichlet BC neural network. And then somehow do a fusion. And this fusion is again a bit of rolling up the sleeves, a bit of engineered. Here is some stacking and summing, and then we have the output. And you can see that in such a Cartesian mesh, we can predict the output sort of, or the solving the Poisson equation with a relatively low error. It's below 10%, so that's better than in run simulations. And it's a big step forward in also making this more efficient and more simple. I wanted to come also to my comfy zone, my comfort zone, which is more in health. We're doing a very broad range of applications of deep learning. And yeah, for this conference theme, I picked the previous two, but a major theme for us is health. I also picked this one because it's in the call for papers of RAMMML, but it's also been one of the topics that has been taking everybody's attention over the last 2-3 years, thanks to COVID-19. And it's a great example of where we need to go with machine learning, because we need to be very quick and fast in providing machine learning solutions. And the COVID-19 crisis has been maybe one of these moments where the machine learning community has been heavily pushed to very quickly come up with answers and help, as everybody else has been. But we needed actually to come up with something that provides benefit. It's not just writing papers, it's a whole different story if you have to do something that's actually useful under super high pressure in terms of time and expectations. Now, in fact, as this conference is taking place in India, I have to say that there has been also great efforts in India. We have been running a machine learning competition, and Indian colleagues have been too, and we have been in great contact with the Indian colleagues. And what we were doing is try to find solutions how we can diagnose COVID-19. It was actually before rapid testing was available at mass. But even now that it is available at mass, of course, we could provide advantages in not causing pollution by these rapid tests and providing easier and instantaneous solutions. Now, how does this work? We needed to do yes or no, COVID-19 positive or negative, with different modalities. So the first one we have been considering was audio. COVID-19 is a respiratory disease, so it should affect how your voice sounds, was the idea, and how your cough sounds. And in fact, yeah, we have been putting together this app. Now, I wanted to give you 3 examples of how this can look like. The thing before we even started with this is that people were looking into chest x-rays and diagnosing with computer vision methods the COVID-19 yes or no and other syndromes, here, for example, CAP. And meaning that you have a computer vision problem, you have to shape a neural network to best do this and train it on data, and from there get some result. We had a very good result, 96.1% from the chest CT, sorry, and X-ray. But of course, this is not fast or anything. You would have to go to some place where you can do CTs or X-rays. With the voice and the audio, it was much more versatile. If you can just speak or cough and some app tells you if you have COVID, yes or no, that is of course very useful. And the machine learning side of this is find something that quickly learns to do that. And what does that mean? It means that we give some audio to a neural network and some labels, COVID, yes or no, and the neural network has to take it from there. In this case, we were using raw audio signals, or we were using spectrograms as a representation. And From that, we need to learn the representation, how to represent the audio, how to find key characteristics of COVID-19 in that with a neural network. Now, these days we have end-to-end learning, for example, with convolutional neural networks. We can do representation learning with deep neural networks, but we still had to shape this network. And of course, there are some templates out there for computer vision problems. There are some templates for computer audition problems, but still, somehow what we need to have is something where you really just take data and labels and throw it at a machine learning algorithm, and it learns to generalize from this data to find new data, even if you're not an expert, ideally in no time, and ideally with very little effort in terms of energy consumption and so on and so forth. Now, what's even worse in the COVID-19 situation at the beginning, of course, is that we didn't have examples to learn from. And you know, this is another key deficiency or drawback of most machine learning algorithms of these hours, that they probably have quite a data hunger. So in the end, this worked. We had our pre-shaped neural network. We trained it at first with very few examples from Wuhan in China, and had some 80+% accuracy for COVID-19, yes or no, from the voice. And now we're revisiting the whole problem with the UK Health and Security Agency with 10,000s of samples, and others are doing this too. Well, I wanted to give you a third example to show the diversity of what you have to deal with, and that is doing the same from your heart rate. So luckily, when COVID-19 started, we had a study running with 10,000s of patients enrolled with a heart rate sensor, a wearable consumer device, a cheap consumer device, getting the heart rate. And some of them got COVID-19, some didn't, so we could see if we can get from these signals also information on COVID-19 or yes or no. Different kind of signal. Again, you can model it as a raw waveform something, or as a spectrogram. And again, you need to find some architecture to best model this. Here we use some autoencoder, and based on the reconstruction error of the autoencoder, we found novelty in the signal, and from that COVID-19 symptoms. Again, this worked very well, so you can see even better than the audio, and this gives us 3 different modalities: images, audio, some sensor signals, very different in their nature. And it gives us 3 very different neural network architectures coming from that. So while it sounds like we can do this easily with deep learning, the reality is that we would want to be better, mostly in not having to have experts involved and a lot of tweaking and trial and error by humans in the loop to shape the network architectures. And on the other hand side, to be able to very quickly learn with few examples and very efficiently to be able in such crises to give speedy responses. Now, with COVID-19 being a health problem, there is coming a lot of further requirements, like pre-processing, of course, separation of sources. There might be other speakers in the background or other things in the images. Then I've already talked about being efficient, but of course you also have to be catering for human needs, like personalize it to users. You also have to deal with drifting targets. Corona was a good example again, because we constantly have new mutations of the virus. So symptoms will also change, and we have to be adaptive to how the whole problem progresses. And then we have to be responsible, a big topic these days in deep learning and AI, privacy, explainability, and so on, fairness are big topics to be discussed these days. Now, of course, it's not only for COVID-19, it's for many further health states, and this is just giving you an idea on what we are working on from these modalities in terms of health. And estimated world prevalences for the diseases that we're working on at this moment makes it every 6th citizen on Earth potentially benefiting from deep learning, being able to sense your health very rapidly in the wild and in real world conditions. Now, final one I picked for today is another big topic for us, and it's saving the environment with deep learning, with different modalities. Again, audio, video, other physical sensors, chemical sensors, and each of which is having their own advantages in terms of data throughput, covered area privacy, richness of information, and so on, costs that it will incur. But the major idea is similar to COVID. We have a real world crisis. And these days we even have new crises that are pressurizing us, and we have to respond quickly to these crises that concern all of us with machine learning. And for all these reasons, we need to be as automatic as possible to not waste much time before we can offer solutions. We have to be very data efficient, because usually when crises occur, we don't have a lot of data samples ready at the beginning, meaning that we have to think of things like transfer learning or other efficient ways of being data efficient that I will talk about. And finally, of course, also efficient in terms of energy that we consume. Coming from that, I wanted to discuss major things that we need to be able to put such solutions together. And this all started maybe in 2000, so the very beginning of the noughties. As a PhD student, I was fascinated by the idea, how should we have deep learning? Well, it wasn't deep learning at that time, but machine learning and neural networks be able to be more automatic, in this sense that you just give data and a label, arbitrary data. You have seen in the examples, it could be video, it could be audio, it could be whatever other signals. And with those labels together, it learns to take it and generalize. So first step that you need, it has to self-learn representation, such that you don't have experts from the domain like audio design, audio features, over thousands, 10,000s, 100,000s of research papers, unbelievable amounts of research costs incurred, and decades passing until we have found as experts the best audio features, respectively the best video features, and so on, but really self-learn the representation. Now, in fact, this is largely being a mission accomplished these days, thanks to deep learning, in fact, because we have the ability to use CNNs, for example, RNNs, to learn the representation. Just from my personal side, we have been doing this for the first time in my favorite domain, which is computer audition. For speech analysis, we have been showing that you can go from the raw audio signals, something that my supervisors during PhD said will never be possible, and completely go from there to analyze the signal rather than having features, but learn even the features. We have been putting this together with visual networks for human health and emotion estimation, and the End2U toolkit, where you can see the QR code here leading you to the GitHub repository, is our solution with a convolutional neural network. And recurrent neural networks, for the front-end side, we use convolution to learn the representation, and for the back-end side for decision-making, because most of our problems are time series, we use recurrent neural networks. But what you can see in this picture is that the audio template network, when we first released this toolkit, now it looks a little bit different, is quite different from the visual part here. The visual one here is inspired from known architectures in the literature, like VGG, for example, ResNet and so on, GoogleNet. The audio part had to be designed by us. And when we first did this, we were shocked how good the self-learning of representation worked, because we had twice as good a result in the end as compared to human-crafted features. But the shock remains that we have to craft, instead of features, network topologies. In the first approach, we were trying to emulate a little bit what humans do in feature extraction for these problems with a network topology. And in the second approach, we simply tried different things and found a configuration that works much better. And now what this tells us is that we have shifted from designing the features and needing experts from the domain to design for audio, maybe male frequency capture coefficients or F0 features. For the visual domain, maybe SIFT features, HAR features, whatever features. We have shifted to, we need experts to at least design these networks, or at least to look into a library where experts have designed these, like we have been picking features from the past. In other words, we need to get rid of this part. And the second question, of course, that arises with this is, can we interpret what the neural network has learned as a representation? Usually, of course, we always have this black box reproach against the deep learning algorithm. And what we can do is correlate the activations, for example, in the neural network with traditional features. We have been doing this for audio, for video, and for physiology signals, and found very high correlations of the neurons in the convolutional part of the neural network with traditional features. For example, in the case of audio with loudness and pitch, which makes sense. So the network has self-learned something which we can understand in the sense that it highly correlates to things that we know. But of course, this is a major problem. In the recurrent neural network part, we can do things like inverse Jacobian analysis to find the timing profiles that have been learned, but we cannot fully interpret, of course, like we could understand the human expert crafted features. So this is one problem we have to work on, and the other one then will be the automation of the design. Just to mention, we have a little bit more that we can visualize and sonify, and because in deep neural networks we're using a lot of attention these days. Think of transformers, for example, and of course we can also visualize learned kernels inside the convolutional neural network. There's a little bit hard to interpret these kernels on the different levels of the convolutional neural network. We can also show attention in time. So there are some things that we can show, but it's maybe quite a bit off in terms of explainability compared to traditional features. When it comes now to shaping the neural networks, of course, there is AutoML, automatic machine learning, dedicated to that. We have been doing this for the first time again in our favorite field, computer addition, where we showed the self-shaping of a neural network that had to learn representation of audio. And we tried it on the interspeech, the largest speech conference crying task. And you don't really need to care about it so much, but essentially what this means is that we had a neural network shape a neural network that then should learn the representation of your arbitrary problem. So coming not only away from designing features, but coming away from designing the networks that should learn the features, such that we really finally fulfill this requirement of just throwing data with a label to a neural network, and it takes it from there. Now, what we have been doing is use reinforcement learning. So the controller network designs the architecture of the child network, and the reward is the accuracy or whatever error you choose here, like in your objective function in the neural network, to measure the quality of the performance of this child network. And based on the reward, the controller has some options to change the architecture. We approached this gently and gave it the opportunity to delete or add neurons in a layer. So we're controlling the size of the neural network. By that, also being able to add or delete whole layers. So deciding on the number of layers. And we also gave it the choice of the activation function. So it could choose things like ReLU, leaky ReLU, and so on, and change the activation function. This is very gentle as an approach because we still have a quantized set of parameters, hyperparameters to change, and it's quite narrow in the sense that there is many more. If you think of a convolutional neural network, you would have the number of filter maps, you would have their sizes, you would have the pooling sizes, you would have all sorts of further parameters to shape and decide upon. But already this worked very well, and in this task, it gave us the best result to have an automatically shaped neural network architecture over the performance of a self-learned representation with a human design network over the performance of a human-shaped feature description. Yeah, so coming away from features designed by humans, the next step being now to come away from the network topology designed by humans. And of course, this all comes as a huge cost of computation energy, already with the largest neural networks being language models, which consume enormous amounts of energy. This comes into question. Can we then even do the shaping of the topology efficiently enough to not pollute the environment? Now, the second step is to be more data efficient. And when we think about pattern recognition, which is what we do in most maybe machine learning problems these days, There is also another side to this, and it is the synthesis of patterns. So for example, when we think of the materials design, this was kind of estimating the quality of materials. So we're doing some recognition problem, classification problem into good or weak properties of our new material. And if we can couple this classification or analysis of a problem with the synthesis of the problem, the idea would be that we're much more efficient. Allow me to give an example again from the audio world, and that is if we speak a language, it's much easier probably to understand the language. We wouldn't learn just to understand the language, we would also learn to speak the language. And then we can talk to ourselves and inside our heads, practice the language with ourselves, with others, and so on, and then can better understand the language. In other words, we should make sure that we're not only looking at the analysis of problems, but also at the synthesis of the problems and then couple the two. I put a challenge accepted here in yellow because we already have some solutions. Generative adversarial networks, for example, are maybe a very obvious example of doing generation of data and analysis of data simultaneously or coupled in some way. So it's not that we don't have this, but we could be more efficient. I chose an example here from the audio domain because we all know of examples from the video domain very well. You definitely know deep fakes, and you know probably that with deep fakes, so images generated with neural networks, you can also augment training material for recognition systems. This is a kind of weak coupling. You generate new data in a way of self-imagination and then use this to augment the training data and then get better in recognition. So I chose audio because it's less common to show audio examples. And what I'm showing you here is our latest quality hi-fi audio generation with colleagues in terms of an adversarial autoencoder. What it has is a little bit different, similar to, again, to a generative adversarial network. You have some generation part, and you also have some classifier part where you give feedback to then be better at generation, and by that also get better at classification. And we're using an autoencoder with an encoder and decoder to do this here. Now, what this can do is imagine, sort of, if you want to, new sounds based on an example of a sound. So what you will be hearing now is generation of audio after hearing one example sound and then taking it from there. So here's an example, and I hope you can hear the audio. So first it got a learning example, and then it generates similar audio in other ways to basically learn to synthesize such audio. Here's a second one. I also had speech examples usually, but I thought it's boring if I only show speech examples where you can have somebody talk with my voice, for example, after having a few words heard. I just give you one or two of those. You hear the first one is a digit uttered by a real-world speaker, and after that, the neural network immediately continues to say other numbers in that voice in the generation.
9, 0, 1, 2, 3.
Okay, let me skip over that. So the network is basically able to do good generation. Does it help to do the recognition then? The usual test to do that is use the generated material for augmentation. So we're using this as additional training data. And here, for example, it is speech recognition, and we get a little bit better by using the newly generated digits as a new training material. So that does work, meaning that it shows that we can generate new data to then better recognize problems, right? So in the case of materials, we would then generate new material constellations that we're imagining sort of as a neural network to then be better able to recognize properties from new materials. That is not the best way to do this yet, because we're explicitly generating training material, use it to augment the training material for then training a neural network to do the classification or regression task. But the ideal thing would that you just do this very in situ, very adapted to your current need. And rather than producing an abundance of training examples and train from an abundance of training examples, you would imagine right on spot how would a new element along or material along these kind of elements look like, and not train a system ready for anything. Rather than coupling synthesis analysis, you could also then go into coupling conversion and analysis, meaning that we're not producing an abundance of examples for arbitrary problems, but we're taking a current example, convert it into a new target state, and then take it from there. So my example here for you is, let's imagine somebody speaks, and the neural network would try to produce this speech in different emotions, and then you could match against a target example. And from that target example, here if this person was really whatever, happy or sad, you could do the same for COVID-19, yes or no, and so on. In other words, rather than producing an abundance of voice examples for a COVID-19 recognizer, for example, to recognize if somebody's negative or positive on COVID-19, we could use somebody's voice and imagine how would that voice sound with or without COVID, and then match it against the current voice and see how we classify him in this situation. I also brought audio examples for you here, and we have a neutral voice first, and then our current state of converting.
At the end of 4.
This is neutral, and in different intensity level, we're getting more and more angry.
At the end of 4. At the end of 4. At the end of 4. At the end of 4.
And I hope you could hear that at the end, the voice sounded quite angry. Same into other emotions from neutral.
At the end of 4.
And I show you very sad now.
At the end of 4.
And from neutral.
At the end of 4.
To very happy.
At the end of 4.
So what this means is that we're coupling analysis and synthesis, or analysis and conversion. So we're kind of using neural networks to imagine how would this sound in different constellations, and then we can match it against the reality to produce our own matched kind of training material. And
at the end of 4. At the end of 4. At the end of.
Sorry, and then get very efficient about that. So the next step then is being more autonomous or more efficient in terms of exploitation of material that is available for learning. And as it is hot off deep learning, I didn't want to talk about all sorts of things, but really focus on self-supervised learning, the current paradigm, and that is probably most popular in deep learning. So rather than doing fully supervised or unsupervised learning or semi-supervised learning, where we still need some label data, we have some task which we can use to train our system into the right direction, and then use it for our actual task of interest, the self-supervised learning. Again, I put this in yellow because basically there are good solutions out there. I could almost put it in green, but it's not across all modalities. It's majorly done in NLP, in natural language processing, and computer vision. And for some other problems, we yet need to, maybe adapt a bit. So what this means is that we have different ways of training a system with existing data that isn't labeled. For example, you could use a picture here, intentionally hide some part of the picture, use some autoencoder or something to try to come up with the original picture, and then measure the loss between the original picture and what you reconstruct after introducing some disturbance. Meaning that you don't need any kind of label, you only need data, and data is what we usually have. So if you want to predict if somebody has COVID or not, we can prepare our system for speech as a modality, even if we don't have labeled speech data. So for the representation learning part, by somehow purposefully destroying information in the signal, trying to recover it, and training a system to do the best recovery. In other words, unlabeled data exploited at scale to get a better representation learning. Now, there is a lot of different ways to do this: predictive and contrastive self-supervised learning, like CME's networks, and clustering also, versus this contrastive SSL, and maybe some known example if you're in NLP is word2vec, for example, where you try to predict a word from the context around. So just as another example, rather than including regions in an image, you could have a phrase and you omit one word, but of course you know which word should be in there, and then train your model to be able to predict this word from everything around. So again, you're just using the existing language, no labeling needed at all, to train a model that is ready to represent language. Different ways to do this. So there's an abundance of ways how you could model this. And this is an overview on current self-supervised learning methods. And what you can see is that the field of research is mostly computer vision. It's a lot of NLP and a little bit of audio. So there's still some work to be done in terms of making this available for other problems, like the material design that I've been showing in the beginning. What you can see from the encoder choice, you have some flexibility, and some have already been tried, like a lot of convolutional neural networks, like ResNets, AlexNets, VGG, and so on, using autoencoders or transformers even. Different loss functions, so you could mix and match pseudo-label strategies here and find your own self-supervised learning method and then exploit the unlabeled data. What we try to do is see, similar to the representation learning, in a kind of self-learning way, if we can imitate features that experts have been crafting by neural networks. This idea has also been followed in other domains. We have been looking into it for audio in particular, and we were training a deep neural network to simulate our audio features from our traditionally run audio feature extractor, and basically found that we have, depending on how much training data we use of speech or audio to train this imitation, we need different network topologies in terms of how many free parameters we can afford. So we're coming back to the problem of we always need to think about how do we get to the architecture of the network. We have been using some mix of convolutional and long short-term memory recurrent neural layers and could imitate very well the features, in the sense that we have been trying with the simulated features or imitated features if you can solve real-world problems. Don't want to go into the details, but maybe just show you some plots where we simulate with a neural network extracting features from traditional feature extractors. And if you have a matched condition of the data, we can get very good estimates here. If you have a mismatched condition, no surprise, it's not as good. But the takeaway is that there's an abundance of abilities to use data and maybe already existent features and not fully discard them, but use them for self-supervised learning and shape neural networks initially, to then take it from there and adapt them and fine-tune them. Yeah, maybe in the interest of time, I will move a bit over this part and just show you one example where we used self-supervised learning for audio-visual speech recognition. In audio-visual, or in visual speech recognition, sorry, not audio-visual, you have to recognize what you have to lip read. You have to recognize what somebody is saying without the audio. And it somehow, this example puts together the things that I've been showing so far. It synthesizes the audio, so it, from the lip reading, so it combines also the idea of generation, to then use this audio to do an audio-visual speech recognition rather than doing a purely visual speech recognition, and uses self-supervised learning coming from the video feed, which is unlabeled, to get better at synthesizing. I just want to give you an example of synthesizing the speech. So we're just looking at the lip movements, and we synthesize the speech. Here we have seen speakers, meaning that we know the person, and basically have constrained vocabulary. This is
place green with L2, please.
The real voice.
Place green with L2, please.
Play green in C5 again. Play green in C5 again.
So as you can hear, because we know the speakers and the vocabulary is restrained, we can produce very, very close to the original speech just from lip reading. Now we have unseen people and constrained vocabulary. Real first.
Set blue by L4 now. It's set to blue by L4 now.
Now it's a different sound of voice because we don't know the speaker and he was whispering, but you can very clearly understand from the lip reading synthesis to audio that it's pretty good actually. Now we have unseen people with completely free audio, and you will again hear first the original and then synthesizing from watching the lip movement.
Body is waiting for the. Waiting for him.
Range of temperatures across.
Lots of temperatures different.
Is our education course.
Is an education council.
The other members of the
Other members of it.
And you see this actually works shockingly good in the sense that you can really from the lip reading synthesize to audio understand what is being said. But what is important is that we also indeed reduce the word error rate by doing this as a self-supervision task. So we're doing the synthesis of the audio and then compare it with the real audio that we have in the original videos to then be better at lip reading, and we highly reduce the word error rate. Next step is green processing, and as I said, all this shaping of architectures, all this self-supervised learning consumes tremendous amounts of energy if you think about really big neural networks. Fortunately, we have very good algorithms for this, so I put it here in green, mission accomplished. I just show you some quick examples, very easy tricks that you can do and that really work miracles already. We have been having this COVID-19 and cold and flu recognizer from the voice into a smartwatch. It can also do other things from the voice, like emotion recognition, whatever. But to put it onto a smartwatch and not run it on a computer, it was enough to use integer values for the weights and activations inside the neural network rather than float, and to prune the network by cutting away those weights which are very low. And that gave us a reduction of 95% in model size, so much smaller models that can be run on smartwatches. We also used partially simply less layers, so very non-intelligent pruning, if you will, cutting out of layers in a neural network for audio recognition tasks, and found that we can go from 24 layers, the original neural network, down to 12, 10, 8 layers almost without any loss in our quality of the audio recognizer. Only when we went down to 8 or 6 for challenging audio tasks, it really broke away a bit. So it's shocking that we can really cut out whole layers after it's well trained and have a much leaner neural network, which works good. Yeah, in cases where we have to be efficient with little training examples which are labeled, because we can train the representation at first in self-supervision or so, but then for the actual classification, is it covered or not, of course we have to have some samples. And from the materials, we have to have some samples to learn about the problem at first, because we can then predict for new material characteristics. Zero and few shot learning are another terms of the hour. And this is marked here in yellow because we already have some algorithms. We need more experience with them and we need more efficient ones maybe, but it's not too bad after all. And basically what this comes down to, and I picked zero shot learning because it's even more drastic, is that you can recognize something that you have never seen as an example before or heard as an example before. Imagine somebody says you should recognize if somebody has corona or not, or COVID or not from the voice, but you never heard anybody with COVID or not. What you're left with is a description of what somebody with COVID should sound like. And then you can check in such a grid here. Here it's recognizing a faulty engine without ever having heard a faulty engine. If these features are present or not. What that means is that we need semantically higher features to then be able from those features to infer if these characteristics are present or not. To do that, it means that we need to produce machine learning algorithms which can self-learn representations, which then, however, are leading to something that you can describe semantically, to then be able to put together a set of attributes that humans can describe, or that at least can be described in some way, to then describe new problems which we haven't seen explicitly in audio, in video, in signal, or that we can somehow describe. In other words, it means that we have to find a way to come from self-learning of representations to self-learning of representations, which then, however, are describable. Let me put it like this. We have been showing this for speech. We could recognize emotions that we had no training example of by describing what a shy person, for example, or a humble whatever person sounds like. This was done by producing representations of the audio signal, which are human describable, human intelligible, and which can then lead to describing what an emotion like this should sound like. We're currently doing this for general audio, so describing what things should sound like and producing attributes that can be described. Now, on an almost final note, this leads us then probably to curious learning. I put here as wanted. There are good algorithms by Jürgen Schmidhuber and others, but what I'm trying to say here is that as we're going more and more into having autonomously shaped machine learning solutions, self-learning representation, self-shaping the architecture to best do so, and then in self-supervision, learning about these things, it means that the next step then would be to have AI, to have deep learning, which is staying curious, to be excited about learning more. And this is a major step then forward to general intelligence, ultimately to be able to have solutions ready when crises occur. This needs to be human-centric at the end of the day, so we shouldn't forget that we're not producing AI for the purpose of AI, but for us, and that is marked here as a must. We have a lot of requirements for deep learning, for AI in general, to be human-centric. It should, of course, be useful. This is a major concern, but it should also be synergistic and complementary, so humans and machine can work together. Then it needs to be explainable, interpretable, and transparent. This is the major deficiency, as I showed at the beginning, for many of the deep learning things, so we need many more efforts there. Should be reliable, efficient, usable, enjoyable, but it also needs to be personalized, private, trustable, ethical, and moral. So a lot of other aspects than the ones that I covered today, which are more focused on the engineering side of making it work in the first place and making it work with little human involvement. So this is reaching the end of this talk, and I just want to use a few seconds to advertise 3 machine learning challenges we're running right now. If you're in these fields by any chance at ACM, multimedia, we're running 2 challenges on audio and video. And at ICML, the International Conference on Machine Learning, we're running an audio challenge. So just if you're interested at all, look at Compare Muse or XVO. And on a final note, deep learning may soon learn largely autonomously for quite general applications. Let's be technically prepared and responsibly design it for you and I. So let's make sure that we're not forgetting all the, the us in the equation when we design even more powerful machine learning algorithms. Thanks very much again for bearing with me, and I hope you could actually hear me till the end. And looking forward to your questions, if time allows.
So thank you very much, Dr. Schuller. It's really a great experience for we people. Up till now, we have a specific limitations as from the mechanical engineering domain. We used to talk about or have practiced fundamentals of function approximation-based neural networks, some classifiers, etc. But the wide perspective which you have portrayed over here, like AutoML and then the future of deep learning, will definitely help us to learn more and more things. Your encouraging word and the direction which you have put forward for we people will definitely help our faculties and our students, sir. So thank you very much. This is my sincere gratitude and sincere thank which I really would like to extend, as we usually have conversation on through mail only, and you gracefully have accepted my invitation to deliver a talk in this particular conference. So big thank you, sir. In nearest future, we are looking forward to associate with you whenever it is possible for us. And depending upon your time frame, we'll definitely need your help in the nearest future to shape the career of our young technocrats, mechanical engineers. Sir, one small question from my side. If we'd like to explore the fundamentals of deep learning for manufacturing, typically for optimization side or to prediction related to the different parameters of manufacturing, what are the possibilities in this particular domain? Your experience, sir?
Yeah, so thank you first of all very much again for the invitation, and very much hoping to having some synergies and collaborations in the future. I think deep learning these days is always great, of course, for simulation and for being more efficient in many ways as compared to traditional simulations. The example maybe at the beginning, or the two examples actually showed this. So learning how to quickly judge things before we have to explicitly produce them or test them probably is a major advantage here. And then the whole idea of generation is not limited, of course, to paintings or music, but you can generate new materials, maybe the next carbine, whatever, coming from a deep neural network could be a reality very soon, right? I hope this somehow answers the question, but what I'm trying to say is it's not only in optimization and simulation and pattern recognition, but maybe even also in generation. And of course, you can always use it in process optimization or things like that.
Okay, perfectly all right. So apart from the speech recognition, natural language processing, and image processing, and high-end audio processing, etc., which are actually the bread and butter, I must say, for the deep learning. From your point of view, obviously, the mechanical engineering may be again a good perspective to apply deep learning for the different set of problems.
Absolutely, yes. I think the ones that you have been mentioning are very popular in the machine learning community because we have the data to toy around with. And this data is intelligible to people who read the paper because they know music, they know images. But now is the time to really go into more specific applications. And yeah, I've shown this for the medical domain, but the same holds, of course, for mechanics, for materials. And there's a lot to gain by using deep learning here.
Okay. One small last question from my side, sir. We are currently working on DICOM images, the CT scan files, which usually converted into the DICOM and DICOM to the 3D printing models. And it is for the pre-surgical operations for the doctors. So we are basically interested in going for the auto segmentation of those images or those DICOM files. So is it possible by using a deep learning process?
Absolutely, yes. So we have 3D CNN architectures very suited for that. So yes, clearly.
It's quite possible.
Yes, absolutely, yes.
Thank you. That's it from my side. Again, thank you very much. I hope if there is any question, participants are requested to please type it down so that Schuller sir may answer it. Sir, I hope there is no question which is picking up right now. So again, thank you very much. I will personally mail you all the details, all certificates and everything. And again, a big thank you, sir, from on behalf of organizing team of RAMMML, on behalf of Department of Mechanical Engineering, and on behalf of Yashwantrao Chauhan College of Engineering, Nagpur, India. Thank you very much, sir.
Thank you, and have a great further conference. Bye.